Okay, let's look at the high temperature limit. So I'm going to argue that the high temperature limit corresponds to Z, which is of course e to the power beta mu, to be less than, much less than 1. Now at first this may seem odd because as t goes to infinity, beta goes to 0. And you'd think that Z then should go to 1. But that's actually not true. What happens, and we'll show this momentarily in a moment, sorry, not momentarily, is that as t goes to infinity, what happens is that as t goes to infinity, mu goes to minus infinity in such a way that that this goes to minus infinity faster than beta goes to 0. Okay, faster. So that what happens is that z then becomes very, very small. So how do we do this? I mean, let's look at it more explicitly. So let's look at the n over v. So what is n over v? N over v is 1 over 4 pi squared 2m. I'm just writing out g explicitly, and then there's 0 to infinity d of e square root of e divided by z inverse e to the power be minus 1. Okay. So, in this equation, we are just, writing out GE explicitly, and I've taken the factor of V to the other side. Now, what you can do is that we can rewrite this, we can massage this equation a little bit. And multiply the numerator by z e to the power minus beta e, so the square root of e, and multiply the denominator by the same thing. So so that'll cancel out this z and this e to the power beta e. So the first term will just become 1. The second term then becomes z e to the power minus beta e. And then what we can say, we can introduce a new variable x, which is beta e. Now, if I introduce this new variable beta e, then my n over v becomes 1 over 4 pi squared 2m by h squared 3/2. Then I factor out this z, and because I have to change the variable, I get a factor of b to the power minus 1/3, but sorry, 2/3, and then we have 0 to infinity d of x e to the power minus x square root of x divided by 1 minus z e to the power minus x. Okay. So now what we can do is that because we are assuming z is small, we can expand the denominator as a binomial series and just keep the leading order term. So if I do that, then it's 4 pi squared to m by h bar squared, 3/2, and then there's a z b to the power of 3/2. We could have taken this inside, and in future we will. And then there is 0 to infinity d of x, and then square root of x e to the power minus x times 1 plus z e to the minus x plus dot dot dot. Okay. Now these are doable integrals. They're doable because if I say u squared is equal to x, then all these this integral and this integral, they all become Gaussian, moments of Gaussians, okay? And that's something we can do. So that should be left as an exercise. And if you do that and do a bit of manipulation, and then also recall the definition of lambda, the thermal de Broglie wavelength, then the expression for n over v becomes Fugacity z divided by lambda cubed 1 plus z divided by 2 square root of 2. Okay. So now this approximation is valid when z is small, right? Which means that this approximation is valid when the number of particles per unit volume is much, much less than the 1 over z cubed. So, which means that the average distance between particles is much larger than the thermal de Broglie wavelength, right? So the average in a space between particles is much larger than the thermal wavelength. Okay. So that means that we can be somewhere in the classical regime, right? Now another thing is that, in the leading order, n over v is constant, means that, because this is constant, because that's what we want to do. We want to keep that constant. Now, lambda has in it a factor of t, well, square root actually. So lambda, so that means that for this to be constant, the fugacity has to be of the order of lambda to the minus 3. But lambda to the power minus 3 is t. And why is that? Because, we want this to be constant, right? But lambda has a factor of 3, so it has to go like t to the power minus 3 by 2. So that means that, as temperature becomes very large, the fugacity is very small, right? Which is something that we assumed before. So we see that our approximation that at temperature is very large, the fugacity is much, much less than 1 is a valid approximation. Now, we can calculate the energy in this approximation, and that turns out to be doing the same kind of manipulations. Now, if I use the expression for n over v to eliminate fugacity, we get the energy, because the fugacity, it has in it mu, the chemical potential, and that's what that's basically what we wanted to eliminate. So eliminate, mu. Then we have 3/2 n over beta, and beta is nothing but 1 over kBt. So we the first term is the term, we recognize it as the ideal gas law term. And then we have 1 over 4 square root of 2 lambda cubed n v. Okay? And this is 3 over PV, 3 by 2 over PV. And therefore PV is n kBt 1 minus lambda cubed n by 4 square root of 2. I think it's V, yeah, plus dot dot dot. Now see that this is the effect of the Bose-Einstein statistics, and its effect is to reduce the pressure of the gas, which is something that should intuitively make sense, because Bose statistics is about, bosons are social creatures. They want to, because of the symmetric wave function, they have no problem being in the same place, and therefore, they have a sort of like natural attraction towards each other, and therefore the pressure is reduced. If these guys were fermions, we would expect that the pressure would be the leading order. In the leading order, the pressure would actually increase because they don't want to be near each other. Okay, so this is the derivation of the gas law in the leading order, and eliminating fugacity. Okay, so any question before we move on to the low temperature discussion?
Well, PV is energy, so are we decreasing pressure or are we decreasing energy?
What do you mean? Oh, right. No. This is what we're saying is that PV, as compared to the ideal gas law, as a classical thing, that the leading order quantum effect is to decrease the leading order effect is to so PV is so okay, is that the energy for the, that's not the energy, right, for the classical gas?
So I think the character of the bosons to stay in the same state lowers the energy of the gas.
Yeah, I think so. Yeah. So yeah, here it's talking about the pressure, but if you keep the volume constant, but if you think of it, the whole thing together, then yeah, it's the energy should be. No, I'm just like, what I'm trying to think is that what was, classic, for the ideal gas, for the monatomic gas, it's what E is. It's 3/2 n
kBt.
yeah, so yeah, it is, yeah, you're right, it is the energy. So yeah, the energy would be, the energy is reduced.
Sir, I have a question.
Yeah.
Why did we differ a new term like fugacity? What does this mean physically, or what advantages do we get from this new term?
It's, I think, as far as I can understand, fugacity is just a very it's big, it's hard to say e to the power z mu all the time. Sorry, e to the power beta mu all the time. So, it's good to give this a name, right?
Oh, okay, got it.
Yeah. And I mean, here, in some sense, yeah. So, yeah, whenever you have something that, it may have other applications, and I'm not sure, but I haven't really seen anything like, okay, let me just Google this and see what comes up. Fugacity literally means the quality of being fleeting or evanescent. Chemistry, a thermodynamic property of real gas, which, if substituted for the pressure or partial pressure in the equation of an ideal gas, gives the application applicable to the real gas. Okay. It just seems like it's a very technical definition. Yeah. So, yeah, I mean, I think in chemistry that probably has other applications, but I'm not aware of that. So, yeah. Okay. Any more questions? Okay. I think I have accidentally closed the back channel chat. Okay, it's open again.